before we move on, salts, if you recall, they are ionic compounds formed by replacing one or more hydrogen atoms of an acid with a metallic ion or an ammonium ion. So in this case, HCl, the H plus in HCl has been replaced by Na plus from NaOH. So giving you the salt sodium chloride. Okay, so acids which are dibasic, for example H2SO4, they can have two hydrogen ions which can be replaced by a metallic ion or an ammonium ion. Okay, so how do you prepare a salt? So why did I mention just now that the topic on acid bases was important? It's because to prepare a salt, the definition already states that you need to replace the hydrogen ions of an acid. So it will be an acid something reaction, acid base, acid carbonate, acid metal, acid something. So these are some of the common acids which we use to prepare salts: HCl, HNO3, H2SO4, sulfurous, and carbonic acid. The more common ones which we use are the first three here. Okay, so for example, if I want to prepare ammonium chloride, so I have to replace the H plus of HCl with the ammonium ion. Magnesium chloride, I replace H plus with Mg2 plus ion. Sodium chloride, I replace it with Na plus ion, and so on and so forth. Then we get a wide range of salts here. And the next question you'll be thinking is, how in the world are you going to separate these salts out from the reaction mixture? Because if you were to react, say, an acid, so let's say inside here you have barium nitrate, and you add in the acid H2SO4, sulfuric acid, because you want to produce the salt barium sulfate. Barium sulfate. So you'll be wondering, how in the world am I supposed to remove barium sulfate from the reaction mixture after I add these two reagents together? So how to remove it? So this is where the topic on preparation of salts prepares you to be able to answer this kind of question and to be able to come up with a method, the most appropriate method to obtain the salt that you want with the reagents. So before we move on, there's something which we need to cover first, because during the preparation of salts, it is quite common. If you recall, you should have done this before, where you react sodium hydroxide together with HCl to get sodium chloride and water, and then you were asked to place this solution over a Bunsen flame and to heat until all the water is evaporated, and this will leave you with your salt, NaCl, behind. But can this be done for every single salt? Actually no. So heating to dryness, this is called heating to dryness, assumes that the salt is thermally stable. It means that if it's heated, it won't break down. If it breaks down, this is a useless method, and that the salt has no water or crystallization. So what is water or crystallization? Basically, if you look at this equation here, this is copper sulfate dot 5H2O. This part in copper sulfate here is called the water of crystallization. We call this hydrated copper 2 sulfate because there's a component of water inside, and this is what we always see in the lab as the blue crystals. If you were to heat copper sulfate, hydrated copper 2 sulfate, you would actually get this white color powder, which is CuSO4. No water present. The water is driven off already. You'll see a white powder. This is anhydrous copper 2 sulfate. So if the question were to ask you to obtain copper 2 sulfate crystals, you cannot heat the solution to dryness. Otherwise, you will get anhydrous copper 2 sulfate instead of the blue crystalline powder, which is hydrated copper 2 sulfate. So what methods can we use to prepare copper 2 sulfate? Hydrated copper 2 sulfate. Later on, we will go a little bit more into this one. Another common example is cobalt 2 chloride. Again, this one here is the water or crystallization. So if a crystal is water or crystallization, you cannot heat it to dryness. And this is actually a very common thing you see in camera boxes. So if you have camera boxes, you will have seen before those little tiny clear balls which are placed in the box to help absorb water vapor from the air to prevent fungus from growing on the camera lens. So when it is fresh from the box, it is usually blue in color. And as the water is absorbed, by cobalt 2 chloride, anhydrous cobalt 2 chloride, it turns pink in color. So when it turns pink, you know that the cobalt 2 chloride has all been used up, all the anhydrous cobalt 2 chloride has been used up, so you need to regenerate this back this way by heating it. Cobalt 2 chloride, the anhydrous version, is also used to test for water, because you see from here, right, when its original color is blue in color. So when you add water, it becomes pink in color. So some papers are impregnated with cobalt 2 chloride, anhydrous cobalt 2 chloride, and when they are exposed to water, the paper turns from blue to pink. So this tells us that the liquid contains water, or the liquid is water. This is a common test which you will use in your QA sessions. Alright, the next thing that we need to know before we can start preparing salts is what kind of compounds are soluble. This table actually appeared before in acid bases, because you need to know what are the salts, what are the products formed which are soluble, insoluble, so you can write the state symbols. So this table has been learned before. If you forgot, please revise. So briefly, all Na plus K plus ammonium compounds are soluble. So for example, if I have Na2SO4, confirm it is soluble because there's Na plus present. If I have K2CO3, it is definitely soluble because there's K plus present. All nitrates are soluble. So anything with a nitrate, barium nitrate, calcium nitrate, anything with nitrate present is soluble in water. Chlorides are all soluble except these two. This is pretty important, so take note. Sulfates all soluble except these three here. Carbonates all insoluble except these three here, which actually are Na plus, K plus, and ammonium compounds. Okay, all lead-2 compounds are insoluble except nitrates. Those with nitrates, because all nitrates are soluble. And all hydroxides are insoluble except those with Na plus and K plus over here. So the solubility table is very important because it allows you to know what is the solubility of the compound, and this will allow you to determine what is the correct method to prepare the salt. If you don't know whether a salt is soluble or insoluble in water, you cannot start with the question at all. So make sure you know this table very, very, very well. Okay, so as I mentioned just now, the method of preparation depends primarily on the solubility of the salt. If it is soluble, you have to prepare it in a more complicated way. If it is insoluble in water, you prepare it in a very simple way. Later we will take a look at this. It depends on how reactive is the metal. So maybe let's say, because from the definition, let's say I want to make sodium chloride. I can replace the H plus of HCl with sodium. Acid metal reaction gives me salt and hydrogen gas. But if you recall, sodium is actually a very reactive metal. So if you put a very reactive metal into acid, this reaction is actually extremely dangerous. So it is not carried out. So what else do we use instead of Na to prepare NaCl? Okay. And last but not least, it depends on the chemicals being reacted together, because you can't use a solid with a solid. Nothing will happen. You also cannot use reagents which will interfere with the collection of the product. So for example, X is a solid, you react with an acid and you get your salt, which is a solid as well, plus water. Let's say plus water. So plus water. So both are solid. What happens if there's extra X left behind? It will actually contaminate your salt Y. And since they are both solids, there will just be one mesh of solids here, both X and Y inside here, and there's no way that you can separate X and Y out. So you need to control for these characters as well, because at the end of the day, what you want to get is the salt with something else that is easily separated. Okay, salt with something else that is easily separated, or salt with water, because water is just water. So let's take a look at the first one, the easiest one, which is the preparation of an insoluble salt. So you see this word here called precipitation. If you recall, precipitation in your QA is the white solid. Say you add NaOH to a solution containing a metal ion, you will see a precipitate here. The precipitate is basically the insoluble compound. Okay, so in this compound is a salt. So if the salt is insoluble in water, very easy. This is the best salt to prepare. Why? Because once you react the mixtures together, A plus B gives you C plus D. If this is insoluble in water, so long as you make sure everything else is soluble, so acid plus something gives you salt plus water, so long as you ensure that everything else is aqueous, you only have a single solid. To remove this solid from all the aqueous solutions, what you do is just to do a simple filtration, and you have your salt collected here in one step. Okay, react two solutions together and you filter the mixture, and you have the salt in one step. So insoluble salts, easiest to prepare. How do you prepare? Precipitation. So let's have an example, barium sulfate. So how do you know it is insoluble first? So this brings us back to the solubility table. So all sulfates are soluble except barium, lead and silver. Okay, so barium sulfate is an insoluble salt. So if it's insoluble, first thing you think, insoluble. So first thing is precipitation. So when you want to prepare something by precipitation, what are the two reagents you need? So the salt is the H plus of acid replaced by metal ions. So what acid do you use? Barium sulfate. So obviously from barium sulfate, you know this sulfate must come from sulfuric acid. And the other component here should come from a reactant which is soluble in water, because this is aqueous. If you get something that's soluble in water and you only have an insoluble salt plus water as a product, you simply need to filter to remove the salt in one step. Okay, so the salt is insoluble in water, right? At the end of the day, you only want one insoluble compound, which is just a salt. So you must make sure that the other reactant which reacts with the acid is soluble in water. So in this case, we can use barium chloride, BaCl2. Or if you want, you can use barium nitrate. All nitrates are soluble. Okay, all nitrates are soluble. So if you are in doubt, just use a nitrate-based compound, because nitrates are confirmed soluble. So how do you do it? Very easy. You have a solution of BaCl2. You pour it into a solution containing H2SO4. Okay, and you will have the reaction which will give you barium sulfate plus HCl. So this is aqueous, this is solid, very easy to separate, very easy, just filter this out, and you have the precipitate as barium sulfate in one step. And because you see there's a solution here, this solution will actually contaminate the precipitate. So you wash with a little bit of water, rinse off the solution here, and then you leave to dry. So at the end of the day, you leave the filter paper to dry, you will get your specks of barium sulfate here, like this. Okay, there's no harm in washing with distilled water, because barium sulfate is insoluble in water anyway, right? So just wash with water and then take out the filter paper and leave to dry. So over here it is press dried between sheets of filter paper and left to dry. So it's a very simple 4-step reaction for you to obtain barium sulfate. Okay, this is the chemical equation I was writing just now. And if you remember how to get the ionic equation, this is the ionic equation. If you forgot, let's do a quick recap. Barium chloride aqueous plus H2SO4 aqueous gives you BaSO4 solid plus HCl aqueous. So the ionic equation, first step is always to write the balanced chemical equation. Okay. The second step is to see which one are aqueous solutions. Which one are aqueous? Because the aqueous, those in aqueous state can dissociate into ions. So I have Ba2 plus, I have Cl minus, and I have two of them. I have H plus, I have two of them as well. I have SO4 2 minus. This one remains because this is the solid, and I have 2H plus here and 2 Cl minus here. So left and right side we cancel out. What can we cancel? We cancel the Cl, we cancel the H plus, and we are just left with this, this, and this. So we merge these three together, the three ions that are left, and what we have is the ionic equation. Okay, Ba2 plus plus SO4 2 minus gives you BaSO4 solid. Alright, try checkpoint 1 by yourself. This is the salt to be prepared. So the salt is, again recap, it's the acid with the H plus replaced by metallic ion or ammonium ion. So how do you prepare this salt? Remember the steps. First step is it soluble in water? If it's insoluble, what method do you use? Then look at the salt's formula. AgCl, which component belongs to the acid? What acid do we use? And what is the other reactant we want to use to make sure that at the end of the day we obtain the salt in one step. Okay, pause the video now to attempt this checkpoint. Continue the video once you are done. Alright, so for the first question, to prepare the salt silver chloride, AgCl is insoluble in water, so this is prepared by precipitation. AgCl, you notice Cl comes from HCl component. Because this is by precipitation, you should choose a reactant here which is soluble in water. So as I mentioned just now, choose a nitrate compound, and you have this equation. Silver nitrate plus HCl gives you AgCl, which is insoluble in water, and HNO3. So you just filter the AgCl out. Lead 2 sulfate is insoluble in water. SO4 must come from H2SO4. So lead component again should be soluble in water. So lead nitrate to give you H2SO4, lead sulfate, and nitric acid. Part C, lead 2 chloride, PbCl2. This is also insoluble in water. This is a white precipitate. So Cl comes from HCl, lead again from lead nitrate, and you have the equation as follows. Last but not least, calcium sulfate. SO4 must come from your sulfuric acid. So you have another component which is soluble in water. So how do we use? Calcium nitrate. Correct. So make sure that we always choose a metal ion component which is soluble in water, because the salt is insoluble. Okay? Alright, so the first method allows us to prepare insoluble salts by precipitation. There's another method which we can use as well. There are a few more methods we can use to prepare different kind of salts. In this case, it is soluble salts. So soluble salts are salts which are soluble in water. So this is a bit more tricky. It's a bit trickier because earlier you can simply filter the salt out. Now, if it is soluble in water, it means at the end of the day you have the salt plus some aqueous substance inside, and you need to remove the salt from this aqueous substance. So of course, the best thing is to have salt plus water, because water is simply water. Okay, but in the instance where we cannot have salt plus water, we must make sure that it is salt plus something else which is easily removed. So what can we do? Right, so there are 4 methods to prepare soluble salts. Acid metal reaction. Okay, acid metal reaction, but of course we cannot react a very reactive metal with acid. For example, sodium, potassium, we cannot do this. We don't react the reactive metals with acid directly. We can do an acid and insoluble base, acid insoluble carbonate, and an acid alkali reaction. This is also called neutralization, if you recall. This is also called neutralization. So these 4 methods here may look a bit scary. Don't worry, we'll go through them one by one. So let's start with the simplest one first, acid with a metal. So if, let's say, you want to make the salt magnesium nitrate, okay? So all nitrates are soluble in water. You know this MgNO3 bracket 2, so this NO3 component must come from HNO3. So where does the Mg come from? So this is soluble in water. Okay, this is soluble in water. So we want to react such that at the end of the day, you have something, you have the salt by itself, and something else which is easily separated. So if let's say we react this directly with magnesium metal, what do we get? We get the salt and we get hydrogen gas. So this is a very good and very clean reaction, because when you react the metal with the acid, you only have the salt. The hydrogen gas simply bubbles away, right? So this is a very good one-step reaction. But the problem here now is magnesium is insoluble in water, correct? So if I add magnesium, so let's say this is the acid here, HNO3. Okay, I add magnesium, I add one piece in, and it reacts with the acid to give me my magnesium nitrate. So this one disappears. I add one more piece in, it reacts with the acid, and it disappears. So I add, and I add, and I add, and as I add, every piece I add, I will see hydrogen gas being evolved in the form of effervescence. I'll see a lot of bubbling. Okay, so as I add and add and add, there will come to a time when all the acid here is completely reacted away, and I still add one more piece in of magnesium ribbon, and this one will not react anymore. Correct? So in this solution here, I have my salt MgNO3, and the H2 is gone into the atmosphere, and I have an extra piece of magnesium. So if you remember your mole concept, this is called excess. This is the magnesium metal is now in excess because there's no more acid left to react away the magnesium ribbon. So now I have my magnesium ribbon and I have my salt. So what do I do to obtain my salt? Very easy, right? I just need to remove the magnesium ribbon. How do I remove it? I filter it out. So I filter this thing out. My magnesium ribbon is left here, and my salt is collected as the filtrate. Okay, so now my salt is here, and the question says I must obtain magnesium nitrate crystals. So how do I go about getting the crystals out from an aqueous solution? Can I evaporate to dryness? Can I evap to dryness? If no, what else can I do? Okay, so what else can I do? So let's go through this bit by bit. Okay, so we only use an acid metal reaction for moderately reactive metals such as zinc and magnesium. So let's have a quick example. For example, we want to prepare zinc sulfate. So this is soluble in water, so we cannot use precipitation. From here, we know that the SO4 component must come from sulfuric acid. The zinc component, we can directly use zinc metal because this is moderately reactive. So we can write the simple equation: zinc plus H2SO4 gives me zinc sulfate plus hydrogen gas. Right? So this is solid, this is AQ, this is AQ, and this is gas. Okay, so how do we prepare? Very simple. We have a beaker containing sulfuric acid, and we simply add zinc powder, spoonful by spoonful and spoonful and spoonful, and we add this to a warm solution. Why warm? Why warm? Because as you increase the temperature, the reaction proceeds faster. Reaction is faster. Okay, so we don't need to spend the whole day trying to make zinc react with sulfuric acid. So we add excess zinc powder. Why excess? So when we add excess zinc powder, we ensure that all the H2SO4 is completely reacted to give us zinc sulfate. So we get rid of all the H2SO4. Correct? Get rid of all the H2SO4. And this is excess. So if you recall earlier, how do we get rid of the excess? We simply filter the excess out. Okay? So when we filter, this is the excess unreacted zinc here, and over here we have the zinc sulfate solution. Now, the next step is the crucial step. How do we get the zinc sulfate crystals out from the solution? We do not evaporate to dryness. We use this method called crystallization. Okay, we use a method called crystallization. So, what is crystallization? We simply heat the filtrate to evaporate off about half of the water. Sometimes you evaporate off about 3/4 of the water. Okay, so when you do this, the solution becomes saturated. So what is saturation? Okay, what is saturation? Basically, saturated solution. So what is the term saturated or saturation? So let's imagine this. If I have a beaker of water here, okay, let's assume that in 100 cm3 of water, I can dissolve 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles of zinc sulfate. Okay, let's say. So if I, and in 100 cm3, I can dissolve max of 10 particles. Okay, so if I were to evaporate off some of the water, if I evaporate off half of it, now this is 50 cm3, I still have 10 zinc sulfate particles inside. But the thing is, 100 cm3 can dissolve 10. 50 cm3 can dissolve how many? It can only dissolve 5. Which means these other 5 here will come out of the solution as crystals. So this is crystallization. Basically, we are evaporating the water off such that there will be extra salt which cannot dissolve in the new reduced volume of water. And this extra salt will appear and it will come out of the solution as crystals. So this is called crystallization. Okay, so we heat to evaporate off half to about 3/4 of the water until the solution is saturated. And then we leave it to cool. And the crystals will gradually form. So once crystals are formed, very easy. How do we get a solid from a mixture, from a liquid? So now this is a solid and liquid mixture. To remove the solid, we simply filter. So once it is filtered off, we have the crystals on the filter paper. Okay, then what do? We have one more step here. We wash the crystals with a small volume of cold distilled water. Okay, so we use a small volume of cold distilled water to wash the crystals, to wash off any impurities and any unreacted, any of the extra solution here. And then we simply leave it on the filter paper to dry. So once this is done, we will have the crystals on the filter paper. Okay, so this is the process of crystallization to obtain a salt which is soluble in water. So let's do a quick recap. Why are crystals not heated to dryness in an oven? If you recall earlier, there's this thing called water of crystallization. Okay, this is to prevent the loss of water of crystallization, if any. Alright, the next method of preparing a soluble salt, is to react the acid with a insoluble base. So again, the salt is soluble. So at the end of the day, we must try to make sure that the reaction mixture at the end of the day only contains the salt with something else. Okay, the salt with something else. So let's say we want to prepare copper sulfate, aqueous crystals. Okay, copper sulfate crystals. So the SO4 component will come from dilute sulfuric acid, and the copper component can come from another compound. Should we use copper metal? No, because copper metal cannot react with acids. Unreactive metal, it doesn't react directly with acids, so we must use something else. Can we use copper nitrate? No, because copper nitrate is soluble in water. So what happens if we add extra copper nitrate in? How are we going to separate this out from the salt, copper sulfate, which is also soluble in water? There's no way, right? There's no way. They are both soluble in water, so there's no way to separate out any excess of copper nitrate if you add excess. So what do? We add in something which, even if you add in excess, it can be easily separated. So something that is in solid state. For example, copper oxide. You can also use copper carbonate. It's also a solid. It's also insoluble in water. Right? So over here, you see, notice, same copper sulfate, you can react with an insoluble carbonate. So once you react the carbonate with the acid, you add excess carbonate, filter the carbonate out, filter the excess carbonate out, you have your copper sulfate in the solution. The next step is to do your crystallization, and you will obtain your copper sulfate crystals. Right? And of course, when you add copper carbonate, one more extra observation you will see during the reaction is effervescence. So when you see the effervescence stop, it means that the carbonate has finished reacting. You can add in more carbonate. Yeah. Okay, the last method here is the more complex method. Actually it's quite a simple method, but this is the most complex of the four, which is to react the acid with an alkali via titration. So what is this method? What is this method? It's because, let's say we want to make sodium chloride. We know the acid component is HCl, but we cannot add Na directly because Na is too reactive. So we must use something which contains Na. And it happens that Na anything is soluble in water, correct? Because all sodium compounds, all Na plus compounds are all soluble in water. So let's just use a base, NaOH. I have NaCl plus H2O, correct? So this is soluble in water, this is soluble in water, this is soluble in water, and this is water. So it means that because this is soluble in water, these two reactants here are soluble in water. If you add excess of one of them, in my final reaction mixture, I will actually have my salt and the excess of either HCl or NaOH. So this contaminates my salt, correct? So in order to ensure that at the end of the day, I only have NaCl plus water, I must make sure that all of this reacts completely with all of this. So they are gone. What is left is just NaCl plus H2O. And then for NaCl, I can evaporate to dryness without worry of any contamination. So to ensure that all the sodium hydroxide reacts completely with all the acid, the method which we use is titration. We can control the volume added, and we use indicators to see when all the acid has reacted with all the base. So let's make a simple salt here, sodium sulfate. So based on the formula Na+, there's Na plus present, so it is confirmed soluble in water. The SO4 component will come from sulfuric acid. The Na component cannot come from the metal because it is too reactive. So you must use something containing Na, so let's use sodium hydroxide. Okay, so we have NaOH here, plus H2SO4, then we get Na2SO4 plus H2O. So this liquid, AQ, AQ, and AQ. So you see this is AQ, this is AQ, this is AQ. So there's no way that we can control exact amounts to be added without any special apparatus or special method. Right? If I add excess of this one, at the end of the day I will have this one, and this one. Right? And there's no way I can separate out the NaOH from the Na2SO4 because they are both aqueous. So, wow, look at the many steps here. Sadly, you must remember every single step here. But this is actually a very simple reaction. This is very simple. Let's describe this with the diagram here. So, first of all, what do you do? First of all, we pipette some sulfuric acid into the conical flask. So the pipette is actually an instrument to allow us to accurately measure 25.0 cm cube of the solution, sulfuric acid, and we put it into a conical flask. So now the conical flask contains H2SO4. I add in some methyl orange indicator. What do I see? Methyl orange is red in acid. Okay, it's red in acid. So I will see a red color solution. Okay, now I must react my sulfuric acid with my sodium hydroxide. So I need to use a suitable apparatus to control the volume of hydroxide added. So in this case, I use this thing which I call a burette. The burette allows me to add the NaOH solution drop-wise. Okay, so by doing this, because H2SO4 methyl orange will show red, when I get rid of all my H+, which means all my H2SO4 is reacted, the solution will actually appear orange in color. Okay, so all the acid is gone, it's no longer red. So imagine this, I have this conical flask here, and the conical flask inside contains H2SO4, H2SO4, H2SO4. Okay, so I add my NaOH in, and I need 2 moles of NaOH to react with 1 mole of H2SO4. So let's say I add 2 moles in, gone. So what is this overall color? It is still red because there's still acid. I add 2 more moles, gone. There's still acid, so this is still red. I add the next 2 moles. Now this is where the critical part comes in. When I add the next 2 moles, this is gone. There's no more acid left. The indicator changes color to orange. At this moment, I know that all my H2SO4 inside has completely reacted with all the NaOH inside. Right? Because if I add one more drop of NaOH inside, there will be NaOH inside, excess of hydroxide, and this color will change to yellow. So yellow means that there's extra NaOH. Orange means that all the acid has completely reacted with all the hydroxide. Both gone. So orange. So I can read the volume used. Maybe let's say this one requires say 50 cm cube. Okay? And I know from here, I use 25 cm cube. So I know that 25 cm cube of acid will react completely with 50 cm cube of base. Correct? So if I know that this reacts with this much, then I can do another titration now without using the indicator, because I know exactly how much reacts already, correct? So I can simply prepare 25 cm cube here, and I add in 50 cm cube from the burette, and voila, NaOH plus H2SO4 using my salt and water. I will know that all my NaOH will react with all my acid, and at the end of the day, I will only have my Na2SO4 plus water left. So once I have the salt and water left, I can simply remove the salt by either evaporation to dryness or crystallization. Okay, so this method here, which you see here, this is called titration. Okay, and there are 11 steps which you need to memorize. So take note of all these steps here. Okay. Right, so this is the overall equation. And if you to do the ionic equation, Na plus OH minus ions, H plus SO4 2 minus, Na plus SO4 2 minus, H2O. So you realize this is simply a neutralization reaction, right? This is simply a neutralization reaction. H plus plus OH minus gives you H2O, neutralization reaction. Okay, now attempt checkpoint 3. Pause the video now to attempt this checkpoint. Continue the video once you are done. Okay, so for checkpoint 3, first question, we don't need to use an indicator when we do acid metal, acid carbonate, or acid oxide reactions. Why? Any idea? Quite simple, right? Because metals are insoluble in acid, carbonates are insoluble, oxides are insoluble. So if I want to prepare a soluble salt, I have acid, I add in my insoluble reactant, I add excess of it, I will simply have the salt here with the unreacted reactant. Then I filter this out, and I can either evaporate to dryness or crystallize to get the salt out. Okay, so what do we do? So why is the answer? So simply it's because we can add in excess, and then we filter off, and we just get the salt from the filtrate. So there's no need to use an indicator to show us that all the acid has completely reacted, because once the acid is gone, my metal, my carbonate, or my oxide will remain in the solution. Question number 2. Each of the following substances react together to produce a salt. So we'll give the formula of each salt form. Which salt is prepared by titration? Which salt is prepared by precipitation? So this one is soluble plus reactive metal component. Precipitation means insoluble in water. Right, balanced chemical equation. Okay, so copper oxide, WHCl, you get CuCl2. This one, you get this one, this one, this one, and this one. And if you take a look through, this is insoluble in water, this is insoluble in water. So you prepare this by precipitation. Sodium nitrate, Na is very reactive, so you cannot use Na itself, you must use NaOH. So to do the reaction between an acid and an alkali, which are both soluble in water, we use the titration method. Okay. Part 4 is quite simple. Calcium nitrate. Calcium carbonate is insoluble in water, so once you add excess of carbonate, it will react away all the acid and be left behind. So your salt is here, your carbonate is here, unreacted carbonate. You simply filter this off, and you have the salt, which can be obtained through your crystallization or evaporation to dryness. Equations, make sure they're balanced. Next question, which one of the following pairs of reagents is not suitable for preparing insoluble salts? The answer is D. Why is it D? To prepare insoluble salts, okay? Calcium sulfate is insoluble. Your other component here, which is your HCl, is H2SO4 plus CaCl2. You get CaSO4 plus HCl. So this is soluble in water. This is soluble, this is soluble, this is insoluble. So very good. You simply filter it out to remove. So this is okay. Aluminium chloride and silver nitrate. So silver nitrate is soluble in water. All nitrates are soluble. AlCl3 is also soluble in water. So to get a salt, you get silver chloride. Silver chloride is insoluble in water plus AlNO3. So everything else here is soluble in water. Okay, everything else here is soluble in water except the salt. So yes, this method is correct. Lithium carbonate and iron 2 sulfate. Lithium carbonate, iron 2 sulfate. We get lithium sulfate plus iron carbonate. Okay, so we get lithium sulfate, iron carbonate. Then you take a look through and you realize that, in fact, your iron carbonate is insoluble in water. This is the salt you want. This is soluble. This is soluble. This is soluble as well. So all three are soluble except the iron carbonate. So you can obtain the insoluble salt easily by filtration. Okay. Lithium is not in the reactivity series, but if you recall, sodium, potassium are. These are all group 1 metals. Okay. All the group 1 metals, they form compounds which are soluble in water. This is a trend. This is a trend. So take note, all group 1 metals, they form compounds which are soluble in water. The last one is barium hydroxide and copper 2 sulfate. So for barium hydroxide and copper 2 sulfate, this is a bit special. Why? So barium hydroxide plus CuSO4, it gives you the salt CuOH2 plus BaSO4. Okay, then you realize that actually, in fact, right, this is insoluble in water and this is insoluble in water. Right, so you have two insoluble salts. There's no way to separate them out. So this is not the correct way to prepare insoluble salts. Question number 4. Which of the following methods is most suitable for preparing potassium chloride, KCl? So we know Cl must come from HCl. The K component cannot be the metal itself because it is too reactive. So you must use K something, maybe K nitrate, potassium nitrate. So this method is confirmed wrong because it's the metal. Add excess solid potassium carbonate to hydrochloric acid, K2CO3 plus HCl. We will get KCl plus H2CO, K plus H2O plus CO2. So can we use this method? Yes, we can, but if we add excess, then we will have the excess of this in the final mixture, because this is also soluble in water, because this is a potassium ion containing compound, right? So if you have extra of this one, at the end of the day you have salt, water, and extra of K2CO3. So this method is also out. Next method, potassium nitrate with sodium chloride, KNO3 plus NaCl. So what do we get? We get KCl plus NaNO3. This is soluble in water. 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 So if I add equal volumes of this and this, equal volumes of this and this, let's assume, assuming that the equal volumes contain 1 mole and 1 mole of this one. Okay, 1 mole and 1 mole of this one. Assuming. But this is not the case, because the volume of this one and volume would not be the same unless the concentrations are different. So for now, for this question's sake, let's assume that the volumes completely react with each other. So we have KCl and NaNO3. So how do we separate KCl out when there's NaNO3 inside, which is also an aqueous salt? So they are both mixed together. There's no way we can get KCl out. So, or there's no way we can get NaNO3 out. So this method is no, wrong. So what we have left is equal volumes of potassium hydroxide and HCl. KOH plus HCl. So if I add KOH and HCl together, what do I get? If I add KOH and HCl together, what do I get? Let's take a look. KOH plus HCl gives me KCl plus H2O. Perfect. So 0.1 mole of this, 0.1 mole of this, they will completely react together. They will completely react, which gives me just my salt and water. And to get my salt, it's simply evaporation dryness or crystallization. Okay, so yes, method D is correct.